412. Again, I'm apprehensive about these videos, so let's just see how it goes. So Battle Creek Cereal is trying a variety of packaging sizes for their Crispy Puff cereal. Below is the list of 6 current packages. So you can see as the packaging gets bigger, it carries more cereal, which makes sense. So write a few sentences to the executives of Battle Creek Cereal that describe the association and give an equation the executives can use to predict the net weight of the cereal, of the cardboard used for packaging. Tell the executives how much cereal an experimental green package that uses 260 inches squared of cardboard expected to hold. So you can see it asks us to do a lot of things here. So what I'm going to do is just sort of bounce back and forth between these two. So here's the data graphed. I went ahead and went into Desmos and I put the data from that table in and then I brought it over into here. So it should look something like this. So first thing we want to do is draw a line of best fit. And again, the line of best fit is the one that goes through the middle. It's not exactly one that hits the most points. So I don't know. I guess I'm fine with something like that. It's, again, yours is probably going to be different, but that's kind of what I come up with. So I have these are going by what, 50s, so I'll call that minus 220. So y equals something x minus, I said minus 220 and then I wrote minus 200, minus 220. I'm looking for lattice points anywhere I can find them. Here's a lattice point right here. I'm looking at 120, 140, 160, 200. And then I'm going to try and find a lattice point as far over here as I can get. Again, it's good to have one on the left side and one on the right side as much as you can get that. So this is going to be 480 and 1100. Oh no, I'm sure that's going to be 1050, right? So that's 657, 758. Yeah, so that's 1050. So I have my slope goes up 850. It goes up. Remember, my change in y to my change in x. My y goes from 200 to 1050, so I went up 850, and my slope goes from over 160 to up 480, so it goes over 320. So I'll go ahead and I'll divide these things. 850 divided by 320. 850. I'm sorry if you can hear the vacuuming in the background. So I get 2.66 about. So we'll say y equals 2.66x minus 220. So what does this mean in context? Well, again, my change in y, I guess I didn't put these here, but this is inches squared of cardboard, right? And the y, if you guys will remember, was the net weight of the cereal. So the x was the packaging and the y was the net weight of the cardboard. So I'm sorry, the net weight of the cereal. So you can see I'm going to have 2.66, what were these, grams? I'm so distracted right now by the vacuum that's getting louder and louder. So 2.66 grams of cereal for every 1 inch squared of cardboard. And that makes sense. The more cardboard I have, the more cereal I can hold. And the y-intercept though, so this is my slope. The y-intercept's weird. It's saying if I have 0 inches squared, 0x is 0 inches squared of cardboard, that I could carry negative 220 grams of cereal, which that's weird. I have no box, but I have negative cereal. So it doesn't have to make sense in context. The example I would tell students would be this. If you've ever been to the beach and you look at the horizon, it looks like that. Well, think about it. The horizon is actually a circle, right? When you look at just a small piece of it, it looks like a line, but we know if we actually made the horizon a line, it would get less and less accurate the further we got from Earth, right? So same thing that's going on here. This line might be accurate where the points are, but it loses accuracy the further it gets from that point, and that's okay. We don't expect it to necessarily always be perfect, but long story short, going through, we did get this equation, and we have figured out what the slope means, and again, more cardboard is more cereal, so again, just sort of shooting through here. write a few sentences. More cardboard equals more cereal is the association. We want to predict how much weight we would have if we had 260 inches squared. So think about it. One thing I could do is go to 260 inches squared and fall over, and you could see that I'm going to be at about 460 grams. About 460 grams if I have 260 inches squared. Or what I can do is grab my calculator and sub into this equation, right? So 2.66 times 260, because I'm saying I have 260 inch squared box, minus 220, and you can see I get 471. Well, just looking at the graph, I was looking at about 460, and my equation says 471. So they both say about the same thing. Again, this is what the this is what the equation predicts, and this is what the graph predicts. So, pretty good on both of them. Pretty pleased with that. Alright, so moving along. It says, interpret the meaning of the slope and the y-intercept of your model in the context of the Battle Creek cereal situation. Does the y-intercept make sense? It doesn't. Like we said, it doesn't make sense to have negative cereal, but that's okay. On 412, it says the residual is a measure of how far the prediction is from what was actually observed. So we're going to take the actual and minus the predicted. So it says the 260 inch squared box in problem 410 will actually hold 355 grams of cereal. So let's go back over here. It actually holds 355. So 355 is about right there. So you can see there's a miss there. And that's what a residual is. A residual is a miss. So again, we were coming up with saying it was actually, was it 355? I've already forgotten. It's actually 355. So this is 355 grams right here. But I predicted too much. I predicted, I'll just go with the 471. So I predicted 471 grams, right? So there's a disparity between my line and the actual, and that's not surprising. If you look at this, my prediction misses most of these points, right? So it's not surprising that there would be a difference. And what they tell us to do is take the actual, and if you'll remember, the actual here is 355, and I'm going to subtract the predicted, and again, my predicted here was 471, and that miss will be called the residual, again, or essentially a residual is a miss. How much did you miss by? So 355 minus 471 is going to give me minus 116. So my residual is minus 116. I'll give you a hint on these. If your actual point is below your prediction line, your residual will always be negative. If your actual point is above the prediction line, it will always be a positive residual. By the way, your residual always goes straight up and down to the line. So that would be the residuals there. So you don't sort of draw your line this way or diagonally. You go straight up and down a vertical line to your prediction line. So that's our residual there. We have a residual of minus 116. We missed by 116. We over predicted what that box would do there. It says, what's the residual for the 471 inch squared box? Well, the 471 inch squared box was 20, 40, 60, 71, was right about here, right? So on mine, my residual was, I didn't really have one. My residual was very small according to my graph, but what I can do is I can use my equation and I can plug 471 in. So again, I have this equation here. I'm going to say 471 times 2.66 minus 220. And again, this is my prediction. So my prediction was 1032. What was my actual? My actual was 1020. So 1020 was the actual, and my prediction was 1032. So actual of 1020, predicted 1032, my residual was minus 12. I barely missed there, and you can see that's That's pretty accurate, and it's pretty true. Like my point is barely below that line. I only missed that residual by 12 to the minus side. All right. So hopefully we're getting a feel for how these residuals work. They can be a little bit tricky. So moving along here, it says the warehouse store wants to offer a supersized 600-inch squared box. The residual for this is 1,005 grams. So let's think about what that means. If I go to a 600 size box, which obviously would be somewhere over here just off. But what's important to remember is they're giving me, and I'm going to clean some of this stuff up if you don't mind right now. So I'm going to go here. I know I've already answered a lot of this stuff here. So I'm going to just leave my equation. Hopefully we know what all this stuff means. Actually, let me clean this up. Okay, so sorry, I just did a little bit of cleaning up over here. So again, we have this. It says a warehouse store wants to offer a 600-inch squared box, and the residual is 1,005. So what's the actual? So we're going to go here, and we're going to say, all right, well, we know 600 inches squared, which again would be somewhere over here. Let's just pretend it's here, right? The actual would be, the actual residual would be 1,005. It'd be way above it, right? Way above it. Remember, 1,005, if it's positive, that means it's above the line. So we'd have a big residual above it. So what would be the actual? Well, we can just use this math. We know the residual is 1,005. We don't know the actual, but we can calculate the predicted by using this equation, right? So we're going to go here. We're going to say 2.66 times 600 minus 220. So we get 1376 as our predicted. So something minus 1376 equals 1,005. So something minus 1376 equals 1,005. I'll just do simple algebra and I'll add 1376 to both sides. So x is going to equal 2381. So the actual is 2381. Ugh, good Lord. Actual is 2381. And again, my actual would be way up here. My residual would be 1,005, which gets me to my predicted, which is 1376. And again, I know this all happens kind of over here, but I'm not allowed to write over here. This won't allow me to. So if we go back over, again, bouncing back and forth, it says, why do you suppose the residual is so large? Well, I don't know if you noticed yet, but I think this whole thing was supposed to be a curve to begin with. I don't think a line was a great fit, and we'll actually look at that in later chapters, in chapter 10, but I hope you see what I'm saying. This looks more curved than it does linear, so I get the feeling that this will be more accurate in the middle than it will be on the ends, kind of like that horizon thing that we talked about, right? The horizon, that line and that curve are both pretty accurate right there, but if you move over here or over here, they become less accurate. Same thing here. The more we move away, the less accurate it becomes. We already saw that with our y-intercept, and now we're seeing it on the other end. It's becoming less accurate. It's more accurate in the middle. All right. It says Armin was concerned about the amount of sugar in his diet, so he went to the store and collected data from several cereal boxes. Armin used the data to create a model that related the amount of sugar in this cereal to the number of calories. S equals 16.9 plus 0.23 C. By the way, you're going to notice this a lot when we do these statistic things, that they change the slope and the y-intercept around. Most of us prefer S equals 0.23 C minus 16.9. So this is indeed the y-intercept. This is indeed the slope. Long story short, I'm going to go ahead and open this up over in here so I can write on it. So give me a second. Here, this is the same as if you wrote it like this. So it doesn't really matter which one, as long as you know that the one with the variable is the slope. So S is the amount of sugar, C is the number of calories. So let's go ahead, first of all, before we even answer this, actually let's do B first. Let's interpret the slope and the y-intercept first. So I know that it's change in y over change in x. And I know my y is the sugar, right? So I'm going to have 0.23 calories in 1 cup of cereal. So 0.23 calories for every 1 x. And in this, we know our x is the c's, or I think I just did this all backwards. Yeah, why does life have to be so hard? Okay, I'm sorry. So this is like y equals mx plus b, right? So our y would be our s's, or the sugar. So 0.23 grams of sugar. I apologize for getting that backwards. So 0.23 grams of sugar for every 1 x, which is a c, which is the number of calories in a cup. So for every 1 calories in a cup. So what we're saying is as our cups go up, we have an extra calories per cup, we have more sugar, which isn't surprising, right? We get more calories, we have more grams of sugar. That's not terribly surprising. So by the way, so that's our slope. So that's what our slope means in context. What does our y-intercept mean in context? Well, our y-intercept means if we have 0x, we have 0 calories in a cup. That would mean we have negative 16.9 grams of sugar. And again, that would not make sense. But that doesn't matter. We're just sort of looking at that instance where it might make sense here, but not here. Also, I would ask you to be as methodical as I was. You can see I was methodical and I still screwed it up. So change in y over change in x, figure out what your x is, figure out what your y is, set that thing up, and then your y-intercept 0 x's and how many y's, and set that up. All right, so now it says, what does a negative residual mean? Well, I have this line, right? I was at negative 16.9 and I have the slope, so this is my equation. S equals negative 16.9 plus 0.23 C, right? This is calories per cup, and this is grams of sugar. So this says, what does a negative residual mean? Well, in this case, a negative residual would be good. It would mean it has less sugar than I thought, right? Less sugar than predicted. Because this is my prediction line. So a negative residual, again, means it's below, so it has less sugar than I thought. I'll tell you, I think sometimes it helps to have a graph, even as ugly as this one is. I definitely think it helps to have the context of what the slope and the y-intercept and what this equation is trying to tell you. Don't take shortcuts and just sort of guess. Actually make sure that you have it right. And again, sorry for my slappy handwriting.